Yeah, good afternoon to all. So today we are going to see some more problems in root locus techniques. So we will see the example 6.4. I feel that it is a very interesting problem. Yeah, sketch the root locus for the system given below with k as a variable parameter and show that the loci of complex roots are part of the circle with the minus 1 0 as the center and radius is equal to root 2. Is the system stable for all values of k? If not, determine the range of k for suitable system operations. Find also the marginal value of k which causes sustained oscillation and the frequency of these oscillations. From the root locus plot, determine the value of k such that the resulting system has a settling time of 4 seconds. What are the corresponding value of the roots? So the given transfer function is g of s into h of s k into s plus 1 divided by s into s minus 1. When you are observing this diagram, you can see that there are two poles and one zero. That is s is equal to 0 and s minus 1 is 0. That means s is equal to 1. Means there are two poles and s plus 1 and open loop 0 is at s is equal to minus 1. So here number of poles n is equal to 2 and number of zeros, that is m is equal to 1. So you already studied that n minus 1, yeah, n minus 1, that means 2 minus 1, n minus m, that n minus m, that means 2 minus 1 root locus that will go from the pole to 0 at infinity. Here there are two poles and 1 0. From one pole, the root locus goes to the neighboring zeros. But other pole, when you consider other pole, it will extend to infinity. Okay, it will extend to infinity. Now, so we will see the diagram first, how the pole, first we will see the diagram, and this is the imaginary axis, this is the real axis, 6.11, and you can see that we marked the poles and zeros. One pole is at a 0 and another pole is at yeah, s is 1. So another pole is at s is equal to 1 and 0 is at s is equal to minus 1. So you can see here 0 at s is equal to minus 1. Now when you are considering the segment before this 0, the number of poles plus 0 on the right half of this segment on real axis only, you should remember that number of poles and zeros plus zeros on real axis to the right of this segment, that is 1 2 3, that is this is an odd number. So what happened is this segment is a part of the root locus. Now when you are considering this segment minus 1 to 0, this is not a part of the root locus because there are two odd number of poles plus zeros to the right of this segment, so it is not a part of. Now between 0 and 1, there are 0 and 1, there is only one pole plus 0 to the right, so it is a part of the segment. It is a part of the root locus. And this is the rule number 3rd, I think that this is a rule number 3rd. And the root locus is symmetric about the real axis. This is the real axis. It is symmetric about the real axis, and as well as the poles and zeros, again it is symmetric about the real axis. That is rule number 1. And we will see once more what is rule number, root locus symmetrical about the real axis. That is the rule number. Each branch of the root locus originate from an open loop poles that already I discussed. Here n is 2 and m is 1. So n minus 1, that is one branch of the root locus will start from pole and it will end at infinity where there is 0 at infinity. Okay, that is explained. Segments of real axis having an odd number of, that is just now I explained. Okay, now we will go according to this textbook. As you can see that all the open loop poles and zeros on the real axis only. Therefore, the root locus is symmetrical about the real axis. The two branches of the root locus start at the open loop poles s is equal to 0 and s is equal to 1, where k is equal to 0, and terminates on the open loop 0 at s is equal to minus 1 and s is equal to infinity, where k is equal to infinity. That means 0 at minus 1 and 0 at infinity, where k is equal to infinity. And third law already I explained. That means part of the root locus, which all of the real axis segments are part of the root locus. Now in order to find the asymptote angle, that is actually it is the 4th rule. 3rd rule already I explained. That can be found by theta q into 2q plus 1 pi n minus m, and here q varies from 0 to n minus m minus 1. n minus m is 1, 1 minus 1 means 0, so q is equal to 0. Now, so this angle of the asymptote is theta naught is equal to theta naught is equal to, here q is equal to 0, so pi by 1, that is equal to 180 degree, the angle of asymptote. Now the point of intersection of asymptote on the real axis is given by, that is the next law. I think that this is not 4th, this is 5th rule. Sum of the real part of the poles. Sum of the real part of the poles are here sum of the real parts of the pole divided by sum of the real parts of zeros divided by number of poles minus number of zeros. Sum of the real parts of the poles, what is 0 plus 1. Then sum of the real parts of 0, that is only 1 0, that is minus 1 divided by 2 minus 1 that is number of poles minus number of 0. So it is 2 minus 1. So we're getting here 1 plus 1, so 2. So the point of intersection of asymptote on the real axis, that is known as centroid, is at plus 2. Now, the root locus exists on the real axis between AC is equal to 1 and AC is equal to 0. AC is 1 and AC is 0. And to the left of AC is equal to minus 1, that is as per our rule number, it is 3, but here it is represented as fifth point. Now, breakaway and break-in points are given by the solution of the equation dk by ds is equal to 0. So this is not a tough. It is, if you know the method, it is very easy to do the problem. Now here modulus of g of s into h of s equal to modulus of k into s plus 1 divided by s into s minus 1 equal to 1. So that is why if you are taking k, this s into s plus 1 go above and s plus 1 will come down. Now dk by ds. Okay. Now dk by ds, d by ds of s into s plus 1, s into s minus 1 divided by s plus 1. So you know how to differentiate this. Denominator as it is, differential of the numerator, this is s square minus s, that will become 2s minus 1, minus numerator as it is, s into s minus 1, the differential of the denominator, that is, you can see 1, that is equal to 0. So you are getting it as s square plus 2s minus 1 is equal to 0. Now, therefore, the break points are given as the solution of this, that is s is equal to minus b plus or minus root of b square minus 4ac, ac is 1 and 1, 4 divided by b, divided by 2a, 2 into 1, that is 2. So when you are solving, you are getting 1 minus 1 plus or minus root 2, that is 0.414, and minus 2.414. So here, since as per this expressions, the root locus exists between s is 0 and s is equal to 1, and to the left of s is equal to minus 1. So here we are getting the breakaway point as 0, 1, 0.414 and minus 2.414. So this will be because these points included the segment on which root locus exists. So we can consider first as break point, s is equal to 0.414, because you know that between s is equal to 1 and s is equal to 0, that is poles. From poles, the root locus starts. So in between this 0.414 is existing. So that means it is a breakaway point. From that means the root locus will hit and spread, divert at a 0.414, and after minus 1, and to the left of s minus 1, after minus 1, minus 2.414 is coming. So this minus 2.144 minus 2 0.414 is a part of the root locus, and this will be because it is after the 0 minus 1 here. S is to minus 1 is the location of the 0, and another 0 we found it in infinity, so we can say that it is a point of break-in point. That means root locus coming and splitting, one will go to splitting and one will go to the zeros at minus 1, other will go to the zeros at infinity. Okay, so yes, now when you're looking into this diagram, we are getting a break point at a point 414. From here it will break away from 2 posts. The root locus starts and it will be breakaway point, and point 2414 is left to this point, so we can say that here is 1 0 and another 0 will be in the infinity, so we can say that it is a break-in point. And this shape that we have to yet to find, but so far we don't know what shape it is, so we'll analyze that. Okay, now next is the break angle at the S is equal to 0.414 and S is equal to minus 2.414 R plus or minus pi by R, that is equal to plus or minus 180 degree by 2, that is equal to plus or minus 90 degree. Here the rules we saw the angle of departure and angle of arrival. Here there is no need to calculate the angle of departure and angle of arrival because the open loop transfer function has no complex poles and zeros. So here all the students, you concentrate that angle of departure and angle of arrival, that last class we discussed. Here angle of departure and angle of arrival, this is applicable only if there is at least one complex zeros or complex poles, then only it is applicable. Here in our problem, as you can see that there won't be any complex zeros and complex poles, so that angle of here when you are observing there is no complex zeros and complex poles, so that is why angle of departure and angle of arrival there is no need to calculate here. Now the point of intersection of the next you can calculate the this is I think the rule number 7 I feel. The point of intersection of root locus with the imaginary axis and the centroid value of k are determined by using the Routh criterion. The characteristic equations 1 plus g of s into h of s is 0. So 1 plus k s plus 1 divided by s into s minus 1 is 0. Now this, you know that this you have to take it to this side, so it will become s square minus s, but ks is also there, so you'll get s square plus k minus 1s plus k is equal to 0. This is your characteristic equation. Now it is this characteristic equation you have to use the Routh stability criterion. So you have to form the Routh table, that is it is a second order, start from s square s1 s, the coefficient of s square is 1, the coefficient of next is k, then s is k minus 1. Now k minus 1 into k, k minus 1 into k minus 1 minus 0 divided by k minus 1, you are getting k here. So here for stability all the elements in the first column of the root array must be positive. Therefore, k should be greater than 0 and k minus 1 also should be 0. That is k greater than 1. So the system is not stable for all values of k. Yeah. So here, for the stability of the element, the first column of the root array must be positive. That means first one is k should be greater than 0. K should be greater than 0. Here k minus 1 greater than 0. That means k should be greater than plus 1. So the system is not stable for all values of k. So when you can see that k greater than 1, k less than 1, it is not stable. So system is not stable for all values of k. Now the marginal values k for the stability is km is equal to this k minus 1 is equal to 0, km is equal to 1. So the range of value of k for the stable systems operation is k must be greater than 1 and less than infinity. Now the frequency of sustained oscillation is given by the solution of auxiliary equations. Now when it is becomes 0, the auxiliary equation is s square plus k. So s square plus k is equal to 0, that where k is equal to km, that is 1. So s square is equal to 1. So s is equal to plus or minus j1, sustained oscillations. So therefore the root locus intersects the imaginary axis when k minus 1 is equal to 0. Okay. So therefore the root locus intersects the imaginary axis at s is equal to plus or minus j1. Hence the frequency of sustained oscillation is omega is equal to 1 radians per second. Now this can be an alternate way. Here we already seen that instead of s square you have to take the characteristic equations. There you have to substitute j omega instead of k. Then you will get, here you will get a minus omega square plus k plus j omega k minus 1 is equal to plus k j omega into k minus 1 is equal to 0. Now you have to see the a real term and imaginary term. That imaginary term j omega k minus 1 is equal to 0. That means omega, the coefficient of imaginary, that is omega k minus 1 is equal to 0. Omega is not equal to 0, k is equal to 1. Now equating the real parts to the 0, minus omega square plus equal to 0. So omega square is equal to k. Omega is equal to square root of k. That means 1 radians per. It is 1. Here omega k minus 1 is equal to 0. So k is equal to 1. Now minus omega square plus k is equal to omega square is equal to, so omega is equal to square root of k, that is equal to 1 radians per second. So 1 root of k, square root of 1, that is 1 radians per second. So any one method you can use. This is the alternate method, but any one method you can use it. I think that this method is so good. This also easy. Any one method you can use it. Now, so here, so far we didn't know that. So here we calculate the angle of departure is 90. That means the angle created here, angle of departure and angle of arrival also 90 degree that we found. Then here we found angle of departure. Then we found that the intersection with the intersection with the imaginary axis here, that is omega is equal to j omega so here we got it as s is equal to j plus o, where is that, s is equal to plus or minus j1, that is the angle of intersection with the imaginary axis, that is plus or minus 1 means plus or minus j omega, that means omega is equal to 1. At omega is equal to 1, we also calculated the value of k, that is equal to 1. At omega is equal to 1, the value of k is equal to 1. So we got the intersection at imaginary axis at k is equal to 1 and omega is equal to 1. So both sides you will get k is equal to 1 and omega is equal to 1. That much we found. But so far we didn't understood or we didn't get the shape of the root locus. For that still we need to work it out. Now for that what we'll do is, I am skipping some portions, this we'll do after this. To determine the loci of complex roots, apply the angle conditions. Angle of g of s g of s into h of s, not h of s, the angle of g of s into h of s is equal to angle of k into s plus 1 divided by s into s minus 1. This is equal to plus or minus 2q plus 1 into pi. Now substituting s is equal to sigma plus j omega in the above equations, wherever s you have to substitute this. The similar type example I had given in the last class. So what you need to do is, you need to substitute here s is equal to sigma plus j omega wherever. So angle of g of s is equal to angle of k, then sigma plus j omega plus 1. S is replaced by, then sigma plus j omega into sigma plus j omega minus 1. Here you can eliminate the k. Now when you are considering this, as you can see here, yes, the same way what we did here, same way in this example what we did here, yes, the same way, sigma plus j omega, this can be a tan inverse of, this k can be removed and remaining thing you have to consider is, so tan inverse, this will be omega by sigma plus, the same way here, in this case, in this case, don't look, this expression may confuse here, k can be neglected, so only this part, this will become sigma plus j omega plus 1. Here the imaginary part is j omega, real part is sigma 1. So this can be written as tan inverse of omega by sigma plus 1. Denominator when you are taking it will become, minus. Denominator it become minus, denominator become minus, that is tan inverse omega by sigma. Then this will become tan omega divided by tan inverse of omega divided by sigma minus 1 is equal to, since here in this expressions there are two poles and one zero, so zeros will be plus pi, these two are minus pi, we already considered that, minus pi, so net effect we are keeping it as minus pi tan inverse of sigma minus 1 minus pi. Now here minus pi you have to take it here, so plus pi tan inverse of omega divided by sigma plus in is equal to tan inverse of omega by sigma plus tan inverse of omega sigma minus 1. Taking the tangent on both sides, okay, tangent, we are taking again tangent, so tan a plus b is equal to tan a plus tan b divided by 1 minus tan a tan b, so tan pi plus tan inverse, that is omega by sigma n divided by 1 minus tan pi omega divided by sigma plus 1 is equal to right hand side that is tan a plus tan b, that means tan inverse, that will be omega by sigma, tan inverse omega by sigma minus 1 divided by 1 minus tan a tan b, that is omega by sigma into omega by sigma minus 1. Okay, now in this case tan pi is equal to 0, so this will become 0, this also becomes 0. Omega by sigma plus 1 is equal to omega, when you are rearranging this, taking the common term, you will get a omega into sigma, so here sigma into sigma minus 1, so here also sigma into sigma minus 1 you have to take it as a common, so omega into sigma minus 1 plus omega into sigma, so omega into sigma minus 1 plus sigma, and denominator you are getting it as sigma into sigma minus 1 omega square, and this all things cancel, you can work it out. Okay, now you are getting like this. Yes, so this you are taking omega will cancel, this you are taking on the right side, so sigma into sigma minus 1 minus omega square, and here 2 sigma minus 1 you are getting here into sigma plus 1 into 2 sigma minus 1. Now again you rearrange it, you will get it as sigma square minus omega square is equal to 2 sigma square 2 sigma square and 2 sigma square, when you multiply 2 sigma square minus sigma, then 2 sigma minus 1, so in that minus sigma plus 2 sigma, so you are getting plus sigma minus 1. Now this all you are taking on the other side, you will get sigma square this sigma if you are taking onto this side, okay, sigma square sigma square minus this sigma square if you are taking on this side, all the terms to this side, what happened, 2 sigma square, and here 1 sigma square is there, so that will be remain as 1 sigma square. Omega square if you are taking this side, that will become plus omega square. This minus sigma you are taking on this side, it will become plus 2 sigma, and here you are having So you are adding plus 1 here, 1 plus 1. So here 1 minus 1 is there. In order to compensate that, minus 1 plus 1 minus 1 you are adding, so that you will get here plus 1, here minus 2. So actually when you are making it, you are getting it as this you are taking to this side, 2 sigma square minus sigma square, you will get a sigma square. This sigma, if you are taking this side, 2 sigma. Then this you are taking on the omega square. Here you are having minus 1, 1 minus 1 is there. But you are adding plus 1 here. Instead of constant, 1 more minus 1 here. So you will get a minus 2 here. That is equal to 0. Now this is in the form of sigma square plus 2 sigma plus, 1 is sigma square plus 2 sigma plus 1 is a second order equation. You will get sigma plus 1 whole square plus omega square is equal to root 2 whole square. 2 means root 2 square. This shows that loci of the complex roots are part of the circle. This is a circle equation with the center is at minus 1, comma 0, and the radius is square root 2. Radius is square root 2. Square root 2 is 1.414. So all of you, just you go back to your PUC or level. What is the expression for a circle? This is the expression for a circle. This is the r square. Okay, and the origin. This is the real part. Then here sigma minus 1. Sigma is equal to, sigma plus 1 is 0. So sigma is equal to minus 1. That is the real part component. And imaginary part component you are getting omega plus nothing is there. So that is equal to 0. So this is the things you should understand.